Si de trouver à manger, si de trouver de l'eau potable et d'avoir accès aux soins. Hier, la présidente du CIC a été elle-même à Gaza. Elle a rendu visite à notre équipe chirurgicale qui opère.
Today we have the pleasure to have Mohammed Kamoun as a speaker in our webinar. Mohammed Kamoun was a postdoctoral researcher at ENT Toulouse, and now he is also postdoctoral researcher in the École Normale Supérieure of Lyon. His research interests lie principally in understanding random discrete structure and mainly permutation and partition. He also interested in permutation patterns. More recently, he became interested in applications of reprobability in statistics. Today, the talk of Dr. Mohammed Kamoun is entitled Universality for the Longest Increasing Subsequence. Thank you again, Dr. Slim, for accepting our invitation, and please, you can start.
Thank you very much for the introduction, and thank you for this opportunity to present some results. So I will be talking about some question that is not new. So the question is, and we try to understand what is the length of the longest increasing subsequence of random permutation. So permutation is just a reordering of the entries from 1 to n, and an increasing subsequence is just some entries that are increasing. One way to see it is the following. So you have your permutation. So for example, this permutation, for this permutation, the image of 1 is 3, the image of 2 is 8, etc. And the question is, what is an increasing subsequence? So an increasing subsequence is, one way to see it is just you look to the second line of the permutation. So you forgot about the first line, and you try to see a sub word that is increasing. For example, here, 1, 2, 4, 5, 6 is increasing. So the object we are studying is the length of the longest increasing subsequence. So for this one, we have 5 entries. And if you try to look to this permutation, it's not possible to find an increasing subsequence of length 6 or more. So the length of the longest increasing subsequence in this example is exactly 5. So as I said before, this is an old problem. So the first conjecture was conjectured by Elam in 61, and he says the following: if you choose your permutation to be a uniform permutation among the n factorial permutation, and you let the size of the permutation go to infinity, then the expectation of the length of the longest increasing subsequence will behave like c square root of n, with the c some constant. So the conjecture have been totally solved in 77. I will say a few words about the proof of Vershik and Kirov and Lugan.
Slim, yeah. I missed something. What is C?
C is some constant.
Any constant. Okay.
The conjecture is that the limit exists.
Okay.
And so yeah, so the C exactly equal to 2. So the conjecture was solved in 77, and so Vershik and Kirov and Lugan proved that this limit exists, and they prove that the limit is exactly equal to 2. And they prove even better is that this convergence holds in probability is not just the average of the longest increasing subsequence behave like c square root of n, but if you take a permutation at random with high probability, you will have exactly 2 square root of n. And why this question became famous in some sense, because in 99 there was an amazing result that says that the fluctuation of of type traceoidum. So this is maybe not very known for a broad audience, but the traceoidum fluctuation appear in many contexts in physics or random matrices. For instance, for example, if you take two matrices, if you take one matrix with entries that are all Gaussian, but complex Gaussian, and you look to this matrix, so the largest eigenvalue will have the same fluctuation than the longest increasing subsequence of random permutation. So this phenomena appear in many models that don't have any obvious link between them. And this is why those questions became famous. And so if you are interested, so you can just look to KPZ universality class.
And what is M star, please?
Just the conjugate and so transpose conjugate.
Okay.
So so you look to M plus M star just to have a symmetric matrix. This guarantee that the eigenvalues are real. This is why they look through this model exactly. Okay, so just I will give you an idea how people prove those results. So we need to look to a more general object that is Young diagrams. So a Young diagram is just a decreasing subsequence of a decreasing sequence of integer that goes to 0, and the size is just the sum of entries. So, for example, if we look to Young diagram of length 3, so we are looking to some sequence that are decreasing, and the sum of the entries are equal to 3. So there are only 3 ones. So 3 then 0, 0, 0, 0, or 2, 1, then zeros, or 1, 1, 1, then zeros. So there is an easy graphical way to see it is just you put some squares. The number of squares is exactly so in the first line you put lambda 1 square. So for example, here we have 3 squares and then 0 square. Here 2 squares, 1 square, then 0 squares. Here 1, 1, 1, then zeros. So does it make sense? Okay.
2, 1 means 2 lines and 1 column. 2, 1, 2, 1, 0. What do you
2,
mean
1, just the first line is 2 squares. The second line is 1 square.
And 0? What means 0?
And then 0 square, so you don't see them.
For the rest, okay.
Yeah.
Okay.
And just a Young tableau is just we will put some entries on those squares. So we will put the entries from 1 to n, but we have one condition on every row we are increasing, and on every column we are increasing. So for example, if we took this shape, so this one will be the 3, 1 zeros. And what does the Young tableau associated to this shape is just the fillings of this Young diagram with entries from 1 to 4, 4 because we have 3 plus 1 equal to 4. And we want that we will be increasing on every line and every column. So here 1, then 2, then 3 increasing, 1, 4 increasing. And there are only 3 ways of filling this Young diagram with entries from 1 to 4, so that we are increasing on every line, on every column. This will be the dimension of this Young diagram. So for example, for this Young diagram, we have 3 possible fillings, then its dimension is 3. So if you are familiar with representation theory, this is just the dimension of the reducible representation of the symmetric group indexed by lambda. But if you don't, if you are not familiar with presentation theory, it's not very important in this presentation. What you need to know is just this equation is that the sum of the dimension, the squares of the dimensions is exactly the size of the group. So for here, n factorial is the size of the symmetric group. And this means that there exists a bijection between the symmetric group. So the symmetric group is just a group of permutations. Sorry if I wasn't clear. And the couples of Young tableau with the same shape. One of these bijections, so there exist many bijections, but one of them is very interesting because it has a link with the longest increasing subsequence that I will present now. So I will show you how to construct one bijection. So it's known that Robinson, as Robinson has said, bijection corresponds to bijection, and I will show you just geometric construction of it. So the first step is you put points of coordinates I sigma I. So for example, here, the first point is 1, 3. So this is 1, 3. The second point is 2, 8. 3, 1, 4, 2, etc. You continue till the final point. And then you start point by point and you shadow the top right region. So the first point was 3, 1. So you shadow this region. You move to the second point, etc. And you will have some boundary. So what you do is just you keep the boundary and you repeat the same procedure with the red point. They are not yet used. So here we shadow this part for the first point. We shadow this part for the second point. And we continue. And we have a second boundary. And we continue till the end. So this will give the first row of the two Young tableau. So, the length will be exactly the number of vertical lines that goes to infinity. Here we have 5 lines that goes to infinity. So we will have 5 entries. And the entries will be the y coordinate of those infinite lines. So here we have 1, 2, 4, 5, and 6. So 1, 2, 4, 5, 6. And for the second tableau, it will be the x coordinate of horizontal lines, vertical lines that go to infinity. So we have 1, 2, 5, 6, 8. Okay. And just the first step will give the longest increasing subsequence because just the number of infinite lines that go to infinity, this is exactly the length of the longest increasing subsequence. So we continue. So with the old boundaries, we have some new corners, and we color those corners with a new color. So I chose the blue for this example. And we do the same thing we did with the red points, but with the blue points. So what we did is the first step, we shadow this region, and we have the first boundary, and the second boundary is by shadowing the region given by these 2 points. So so the y coordinates of horizontal lines will give me the 3, 7 that are here, and the x coordinate of vertical lines will give me the 3, 4 that are here. And I have a last point, this black point, and I continue. I will have the last entry of my Young tableau. So now I have dashed the image. There are just two Young tableau of the same shape. So this is the projection I told you before. So this is a one-to-one correspondence between permutations and pair of standard Young tableau of the same shape. And what is really interesting in our case, not the entries, but that's just the shape. So we can forget about the entries. What is interesting is the shape. And as I told you, the first line exactly, so its length is exactly the longest increasing subsequent of the permutation. So there is a way to understand the the length of the other lines. So this is a theorem by Green that says there is some recursive way to construct them. That is the following. So if you denote by I1 the set of increasing subsequences and IK just the sequences you get by concatenating two increasing subsequences. So for example, in this example, so what are the increasing subsequences of this permutation? So we have the empty set, but the image of 1 and 2 are increasing, so it's just 2, 3. The image of any singleton will be an increasing subsequence, and so the only increasing subsequences are these increasing subsequences. But if you allow to concatenate two increasing subsequences, you will have all subsets of 1, 2, 3. And so what is the description exactly of the other lines is the following. So if you so the length of a maximum element of S of I is exactly the sum of the K first rows. So to say it in other words, if we go back to our example, so here we have the longest increasing subsequence is of length 6, but if you take two increasing subsequences, you can have two together to have an increasing two increasing subsequence. The sum of their lengths will be 5 plus 2. So here in this case, so if you look to this one and this one, so if you concatenate those two, so 3, 7 is an increasing subsequence, 1, 2, 4, 5, 6 is an increasing subsequence. So their length is 7, and it's not possible to have two increasing subsequence with the sum of lengths equal to 8. So this means that lambda 1 plus lambda 2 is equal to 7. And we had before that lambda 1 is the length of the longest increasing subsequence, that is 5. This gives that lambda 2 is equal to 2. This is the 2 we see here. I hope it was clear. Okay. So we have almost finished the introduction of the object. So now we'll see our Young diagram after some rotation. So this is exactly our Young diagram, and just we rotated it. So this was lambda 1, this is lambda 2, so this is lambda 3, and we'll see just the high function. So what Vershikant, Kirov, and Logan proved is just if you see this shape, this will give you for n big enough some deterministic shape. So if you take a permutation with a large permutation at random, so the shape will be like this with high probability. So why this solves the problem? So because the longest increasing subsequence is just, we see it here. And this exactly 2 square root of n. So what they prove a result that is much stronger than just the longest increasing subsequence would behave typically like 2 square root of n, but they really prove something like if you take k increasing subsequence of maximum length, then their length, the sum of their lengths will behave like 2k square root of n. And for the proof of the fluctuation, so this is what people call determinantal processes. So the idea is just, it's possible if you look to lambda I minus I, when the permutation is uniform up to some randomness, up to adding some randomness, this probability can be written like a determinant of some kernel, and this kernel have some nice probability properties because it converges to some known kernel that is the Airy process. So I will not go through details, but just what I wanted to say here is that all the proof depends that the permutation is uniform because you have this bijection that I told you before, and it's not possible to apply the same technique for any other non-uniform permutation, because what happens is that if you have a bijection, you can forget about the initial problem and study a totally new problem. And if it happens that this new problem you can do the calculus easily in this new problem, that's okay. So this is what happened here. So what I try to do is just to generalize those results for some other classes of permutation that are not at all uniform. So the permutation I'm interested in, they have some property, that is called conjugacy invariance. So that means that for any permutation rho sigma n, rho minus 1 have exactly the same distribution that as sigma n. Why it says conjugacy invariance is because one typical example of those permutation is a permutation picked uniformly in a conjugacy class of the symmetric group. But there are other models that came from biology. So the first one is known that the ENS model. And just for this model, you put some parameter theta, power the total number of cycles of the permutation, and you divide by some normalization constant. So this model appear in biology. So for mutation, and every cycle will represent the population that have some property, for example, the color of eyes or something like that. And there are other generalizations that depend of cycles of length I, and so this class is really very, very large. And what we can prove is the following. So if the permutation is have this invariance plus some technical control on the total number of cycles, then we have exactly the same properties that I showed you before. So we have a fluctuation of type traceoidal. We have that the longest increasing subsequence will behave typically like 2 square root of n, and this shape I showed you before will become the same. So while looking to non-uniform models, so our study was motivated by some conjecture on the longest common subsequence of IID permutation. So So this problem comes from computer science, and the question, suppose you have two different files and you want to see if they have some common part or just the common part is random. So, for example, to detect plagiat or other question like that, or suppose you have many versions of the same file, and you want to decide if those versions came from the exact same file or not. So the motivation came from computer science, from a mathematical point of view. So suppose you have a finite alphabet, A1, A2, AN, and you have a word using this alphabet. So suppose you have two words, and you want to see what is the length of the longest common subsequence between the two. So for me, what matters is exactly the order. So for example, here 145 is a subword of omega 1 and omega 2. So this is a common subword of length 3. And if you look carefully to those words, it's not possible to have a common subword of length more than 3. So the longest common subword is of length 3. And so in this direction, there are many conjectures that are easy to state, but they are not even known. So even in the easiest case, so you took two words using only the letters 0 and 1, so binary words. So in this case, or an alphabet of length J, in this case, it's not difficult to show that the longest common subsequence will behave like some constant some constant times n. But this constant is not known even in the easiest case, even in the binary case. So the best known boundaries of that is between 0.78 and 0.82, but no one know how to solve those problems. So there are some control when the size of the alphabet goes to infinity, but no exact results. So what is the links to the longest increasing subsequence? So the links, we have a link only in the case of permutation. So when the words are permutation, it means that the words don't have repetition in the entries. So we define exactly the same way the longest common subsequence of two permutation, like we defined it for words. So we look to the second line, and we look for a subword that is common between the two permutations. So for example, here 145 is common between the sigma and rho. And the links to the longest increasing subsequence is the following. So for any three permutation, it's not difficult to see that the longest common subsequence of sigma rho is just exactly the longest common subsequence of sigma tau rho tau. And if you choose tau to be sigma minus 1, so we'll have then the longest common subsequence of sigma rho is exactly the longest common subsequence of sigma rho minus 1 and the identity. And for the identity, what you have is that all the subsequences of the identity is the increasing subsequences. So the longest common subsequence of sigma rho is exactly the longest increasing subsequence of sigma rho minus 1. So to understand the longest common subsequence, you just need to understand what is the longest increasing subsequence. And so the big conjecture in this domain is the following. So if you take two permutations that have exactly the same row, that are of size n, then the expectation of the longest common subsequence is greater than square root of n. So I want to emphasize that for any law, so the conjecture is for any law, this holds true. It's not only for the uniform case. So for the uniform case, it's easy to prove, but the conjecture is if you take any law on permutation, any random way of picking the permutation, this conjecture will stay true. So we can see it as a conjecture on the longest increasing subsequence, as I told you before. So it became just the expectation of the longest increasing subsequence of rho n, sigma n rho n minus 1 is greater than square root of n. So at first, people were thinking that maybe the uniform law minimize this object, but Audrey and Xu proved give a counterexample and prove that this the longest common subsequence is not minimized in the uniform case, but they believe that the uniform case minimize this object in an asymptotic way. And for the moment, the best known bound is cubic root of n. Okay, so what we proved is the following, is that this conjecture holds true for conjugacy invariant permutation. So we didn't solve the conjecture in the more general case, but if the law have this conjugacy invariant, then the conjecture holds true. Exactly what we proved is there is some n0 such that for n greater than n0, so that this n0 will be like 63. And for n greater than 63, if you take any two random permutations that have the same law, but we add the condition that they are conjugacy invariant, then the expectation of the longest common subsequence is greater than square root of n. So I will just give you some hint on the proof. So if the law of the permutation have two match fixed points, then it's possible to construct a common subsequence using only fixed points. Otherwise, so you can use the result I presented before on the longest on the shape to see that the shape will be exactly the shape we had before. So for the result of Vershik and Kirov and Lukan and Chep, and so all this machinery is like if you understand what happened for a general model for the longest increasing subsequence, you can understand better the longest common subsequence. And so the technique we developed can easily be generalized even if the two permutations don't have exactly the same law. So for example, if the first permutation, the two permutations are conjugacy invariant, but they don't have exactly the same law, it's possible to show that at least the expectation of the longest common subsequence will be like 121 square root of n. And so even if one of them is conjugacy invariant and the other is not, so it's possible to extend the results to give lower bounds in all the cases. So even if those objects look difficult, so all those results came from this shape I showed you before, because so for example in this function you recognize this shape, and this shape was exactly the shape I showed you here. So the function is just exactly the limiting shape of this. So, this is to say that this bijection is really important even in the non-uniform case where we don't have exact control. One other aspect of the work that I showed you, that we can also see what are the fluctuation of the longest common subsequence of two permutation to IID permutation that are conjugacy invariant. So if they don't have a lot of cycles, then we have the famous Tracy-Weldon fluctuation I showed you before. And if they have at most square root of n cycle, then the longest common subsequent will behave like 2 square root of n in expectation or in probability independent of the control you impose. And thank you for your attention.
Thank you, Dr. Kamoun, for this nice talk. Are there some questions, please? Some questions, please? Yes.
Perhaps I missed something, but when you give the result about the longest subsequence for two common words, did you give also an algorithm to find this largest subsequence, or is it just properties of this largest subsequence?
So one way to program it, even if it's not really optimal, so you can use this property. So the longest common subsequence of sigma rho is just the longest increasing subsequence of sigma rho minus 1. And so step number 1, you calculate what is sigma rho minus 1. And step 2, you apply this, what I showed you here. So the number of steps will be exactly the longest of the longest increasing subsequence of sigma rho minus 1. So this will give you the longest common subsequence of sigma rho. Does it answer your question or not?
Yes, yes, of course. Yeah.
Other questions, please? I have a question, Dr. Slim. This model is not very related to the problem of Moran random walk. A walk where we go up, we go up by one step with some probability, and with the complementary probability, we reset to 0. And we study the height of this walk, the longest altitude of this, the biggest altitude of this walk. Is not a problem very similar to use or not?
So it's not exactly random walks, but something that is in the same flavor than random walks. So this is called the last passage percolation problem. Are you familiar with that?
Yes.
So suppose you have some points and you want to go from 0, 0 to 1, 1, and you are only allowed to go up, right? And
yes,
you want to collect the maximum number of points.
Yes, not exactly the maximum number of points, but the maximum of altitude of this world.
Yeah, as I said, it's not exactly related to random walks, but like to last passage percolation. So yeah.
Okay. Because this random walk has altitude in in average around log n. It's not the square root of n.
Exactly.
So
But
certainly it's not the same problem.
yeah,
Yes.
exactly. But so not the problem exactly related, but the tracing fluctuation appear also in random walks, but in what called random walks in so I would say it in French because I'm not sure how to say it in donc les marches aléatoires dans des environnements aléatoires. So random walks in random environments. So yeah.
Okay.
So yeah, the same type of fluctuation appears, but I'm not sure if there is a direct link to this model.
Yes, sure. Yes. And we have some results about LCS, last longest common subsequence of two permutation. We can generalize this for more than two permutations or not? Sigma prime and sigma second. Can us have the same results, some results without difficulty?
Yeah. So this is a very difficult question because so to understand the longest common subsequence of multiple words that are not permutations. So people try to do it and they have some bounds, but they are not at all optimal. But for permutation, the question is even more complicated. So I know that at least Christian Audrey, who is working in the United States, who tried to understand what happened, and we had many discussion on this question, and it's a very complicated question because so for permutations to solve the problem we go through the longest increasing subsequence, but for three you don't have this description exactly. So there is no easy way to understand exactly the law, at least from what we know at this moment. So it's a very interesting and complicated question. Yeah.
Okay. And for the longest common subsequence of two permutations, cannot be related to some random walk. The problem of LCS of sigma 1 and sigma 2 cannot be viewed as some specific random walk. And so we study the height of this random walk.
So there is one link that is not easy to explain, but it's related to so non-intersecting random walks. Not exactly random walks, but so you have so suppose you have some alphabet 1 to k, and you want to look to what is the longest common subsequence of two words that is picked uniformly. This is like picking k random walks that start from positions 0, 1, 2, k, and the condition that those walks don't intersect till time n. So there is a link to random walks, but with some conditioning, and yeah, it's not obvious as link, but the link exists. Yeah.
And sure, there are some. Yes, sorry.
No. Just what I want to see, if you are interested to this, so maybe you can see the works of Christian Audrey on this matter.
Okay. Okay. And sure, there are some applications in biology when we study the DNA. When we study the specific DNA, if there are some similarity between some kind of DNA, your work can be applicable in this area.
Yeah. So if you have two sequences of DNA and you want to see how similar are those sequences, yeah, this was one of the motivations to look to the longest common subsequence. But so in this case, So you have an alphabet only of 4 letters because you have only C, T, G, and A. So the possible
Okay.
entries, but yeah. Not in the case of permutation, but in the case of words, this was one of the motivations to look to this model. Yeah, thank you. Thank you for the comment.
Are there other questions, please? Where comes the normalization and power 1/6? Just
Oh, so this is very, so it's really difficult to explain because so this is very common to the KPZ universality class. So all those models where Tracy Widom appear, what happened is so you have something that is some particles that have a strong correlation, and the fluctuation is less than square root of n. So maybe in the case of random matrices, this is more easy to see. So so if you take a matrix with some random entries, and if you change one of the entries by one, the eigenvalues don't move a lot. So the eigenvalues are somehow rigid to perturbation. And so this is what happens also in those models. If you perturbate the entries of the permutation a bit, then the longest increasing subsequence don't move a lot. So so what you expect in general, so if you have the longest increasing subsequence of order square root of n, so you expect that the fluctuation will be n1/4, so the square root of n, but it's really less, and this is very specific to this what we call the KPZ universality class here.
In example 2 here, sorry, listen. In example 2 here, what do you mean by theta I to the power cardinal I sigma? What is I here? Cardinal of I sigma. What do you mean by cardinal of I sigma? In example 2, in this slide.
Oh, so this is just
Sigma I.
sigma. So this is the number of cycles
Of sigma.
of length I of sigma.
Okay. Okay. Other questions?
Yes, please.
Yes, we sent.
Could you please go to page 5, Slim?
Yep.
Fine.
Before, sorry, maybe 3.
This one?
This one, yes, sir. In the second theorem,
Yep.
there is a redundancy, right? You have convergence in L1 and then in probability.
So the first one is not in L1, just the expectation. So it's really less because the expectation goes to 2, but it doesn't mean that it goes in L1 to 2.
You have the expectation of the sequence of positive random variables.
Yeah.
And the limit of the expectation of xn goes to 2, right?
Yeah, but so this is, so the convergence in L2 means that you have this
Absolute value.
An absolute value, right, like that.
So this is weaker than the convergence
Bigger,
in
this is
L1.
bigger, right?
So the constant C is equals to the conjecture of ENS.
So the conjecture, so the first conjecture, ULAM don't know how the constant looks like. So it was just a conjecture that these objects converge.
Okay. Other questions, please? If not, we have to thank again Dr. Kamoun for this nice talk and nice topic. And see you after 2 weeks. Thank you. Thank you, Slim.
Thank you.
Merci beaucoup.
Merci, Slim.
J'arrête l'enregistrement.